The last concept in this section involves the multiplication rule for the probability of A and B. The probability that two events A and B will occur in a sequence is always given by this formula. You can calculate the probability of A happening and then B by using one of these two formulas, depending on whether you have dependent or independent events. If your events are dependent, you're going to multiply the probability of A happening times the probability of B given A. Since these events are dependent, the probability that B happens is affected by what happened first, event A. In the second bullet, you can see when the events are independent, meaning one does not influence the probabilities of the second one happening, then you just multiply those two probabilities together. So let's look at some examples. Two cards are selected without replacing the first card from a standard deck of 52 playing cards. Find the probability of selecting a king and then selecting a queen. So if king is my first event and my second event is selecting a queen, first I need to decide, are those independent or dependent events? Since we don't replace the first card, as we've seen in previous examples, that is going to affect the probability of what happens after that first card is taken out. So therefore, these events are going to be dependent. So in that case, the multiplication rule says the probability of getting a king and a queen, which you can write this way, or you can use the letters A and B as we've set them up, is equal to, and we're going to be using the first version of the formula. If you follow the formula using K and Q as the notation for king and queen, then the probability of this happening is the probability of getting a king times the probability of getting a queen, given that my first pick was a king. Or if you are using the A and B notation, you would write it as the probability of A happening times the probability of B given A. Now, most often I kind of prefer doing this rather than using the generic A and B, but really it's whatever you're comfortable with. So in order to get my final answer, I need to calculate these two probabilities. The first probability is just straight up, what's the probability of getting a king out of a deck of cards? Well, there are 4 kings in the deck of 52 cards. Multiplication rule says I'm going to multiply that by, next, the probability I get a queen, given that a king was chosen the first time and not replaced. Well, there's still 4 queens in the deck, but now there's only 51 cards. So you would multiply these together, numerator times numerator, denominator times denominator, or use your calculator, and you're going to get 16 over 2,652, or approximately the decimal 0.006. So what that's telling us is that this is not a very likely event to happen. Suppose we have a coin tossed and a die rolled. Find the probability of tossing a head and then rolling a 6. As we said before, these would be considered independent events because what I get from the coin toss has no impact on the probability of rolling a 6. So therefore, going back to our multiplication rule, I'm going to be using the second form where I just need the individual probabilities, and since they don't affect each other, I just take those numbers and multiply them. Rather than use A and B here, I'm going to say I'm trying to determine the probability of tossing a head, H, and getting a 6. So according to the multiplication rule, I just need to multiply those individual probabilities. Probability of getting ahead when I flip a coin is 1/2, one out of two possible outcomes. I can get heads or tails, only one of those is heads, times the probability of rolling a 6. Well, there's 6 sides to a die, and only one of them is labeled with a 6. So I multiply these fractions together, I get 1 over 12, or approximately 0.08. All right. Example 4 is just another example of using multiplication rule, and it's talking about ACL reconstructive surgery, which is a form of a knee surgery. Suppose that the probability that the surgery is successful is 0.95. So that's pretty close to 1, so that's pretty likely to happen. And again, this might be a subjective probability that the doctor that's his educated guess as to the success rate, or it's possible that there has been a study performed to collect data. We're not told which one it is, but it doesn't affect how we approach the problem. So find the probability that 3 ACL surgeries are successful. So the multiplication rule does not have to be limited to the probability of finding just 2 events happening one after the other. We can use 3 different events, 4 different events, 5 different events. It doesn't matter. So first of all, we need to think about, is each surgery an independent or a dependent event? Does this first surgery, the success or failure of that, affect the outcome of the surgery for the second person? And the answer to that is no. Those are independent events. So, really, what I'm looking for here is the probability of a success and another success and another success. And the multiplication rule says I would take the individual probability of success on each surgery and just multiply those together to get my answer. So in other words, I'm going to be taking 0.95 times itself 3 times, or again, you can choose to write that in exponential notation as 0.95 to the third power. And when you calculate that value, you should get approximately 0.86, or an 86% chance that 3 surgeries would be successful. So that's pretty good. So in number 2, we're asked to find the probability that none of the 3 surgeries are successful. So I would want to calculate the probability of a failure, followed by a failure, followed by a failure. And since these surgeries are independent, that just means finding out what the probability of failure is and multiplying it times itself 3 times. Now here we want to remember our rule for finding the complement of an event. So if we know the probability of being successful was 0.95, then the probability of not being successful, which is the same as a probability of a failure, is always 1 minus the probability of the complementary event, 1 minus the probability of success. So if you do 1 minus 0.95, you get 0.05. And that should make sense, because if your rate of success here is a 95%, then rate of failure is 5%. So to get our final answer here, we're going to take 0.05, multiply it times itself 3 times, and we get a very small number, 0.0001. So the chance that none of the surgeries would be successful is very small. Now, find the probability that at least one of the 3 surgeries is successful. Okay. Well, in the last example, we found the probability that none of the surgeries were successful. That's the number that we found here. At least one means either there was only one success, or there could be two successes, or there could be three successes. So we need to count all of those. So the only thing that's not on this list, if we're doing 3 surgeries, what can happen? Well, you can get one success, you can get two successes, you can get three successes, or the other thing that can happen is you get none. These are, in essence, opposites of each other. The complement of at least one, the only thing that's left out is none. So if we want to find the probability of at least one success, our rule for complement says we can do 1 minus the probability of the complement, which is the probability that none are successes. So I do 1 minus the number that I got previously. Again, this is an approximate answer of 0.9999. Now that's very close to 1. So what that's telling us is it's extremely likely that at least one of the 3 surgeries would be successful. All right, and a last example. In a recent year, there were 18,187 U.S. allopathic medical school seniors who applied to residency programs and submitted their residency program choices. Of these seniors, 17,057 were matched with positions, with about 79.2% getting one of their top 3 choices. We're asked to find the probability that a randomly selected senior was matched with a residency position and it was one of their top 3 choices. So in this case, I have 2 events taking place. I'm going to call the first one M, and that's going to be the event of being matched with a residency position. And the second event is that it happens to be a match with one of the top 3 choices. So I'm going to use 3 to represent matched with a top 3 choice. Now, I need to determine if these are dependent or independent events. Specifically, I want to know whether or not their chance of getting matched with a position depends at all on them being matched with the top 3 choice. So I'm going to want to calculate the probability of getting a top 3 choice given that they did get a match, and I want to calculate just the probability of being matched. And by comparing these, I'll know if these are dependent or independent. So I'm told that the probability of them getting one of their top 3 choices of those who were matched was 79.2%, which is the same as the number 0.792. I would just divide by 100 to get that decimal back. What's the probability of them getting a match in the first place? Well, here's where you've got to think about it. The probability of getting a match, how many people did it happen for? It happened for 17,057 of how many total seniors? Well, that was 18,187. So if you divide those numbers out, you get the probability of being matched at all to be approximately 0.938. So because these 2 numbers are different, because the probability of just being matched did not equal the probability of a top 3 choice given that they did get a match, we know that these are dependent events. that somehow whether or not they got their top 3 choice did depend partially on whether they made a match in the first place. So now that I know that, I'm asked to find the probability that a senior was matched and it was one of the senior's top 3 choices. So I'm asked to find the probability that they were matched and got a top 3 choice. Because these are dependent events, that means I'm going to calculate the probability of getting a match times the probability of it being a top 3 choice, given that a match was made. I know P of M, I calculated that up here. And when you use that value, it is better to use the fraction rather than using the decimal because the decimal's been rounded and that's going to introduce a rounding error. So for P of M, I'm going to use the fraction version. For the probability of 3 given M, I'm going to go ahead and use the decimal 0.792. And when you multiply these two together, you get approximately 0.743 or a 74% chance. So we know the probability of a senior being matched and that match being one of the senior's top 3 choices. So in number 2, we want the probability that a randomly selected senior who was matched with a residency position did not get matched with their top 3 choices. So remember from up above that those who were matched had a 79.2% chance of getting 79.2% chance of getting a top 3 choice. So if I want to know what's the probability that they did not get matched with one of their top 3 choices, this is the complement. So in notation, what I'm trying to calculate is the probability that they did not get a top 3 choice. So see how I have the 3 prime here, given that they were matched, and that's supposed to be 1 minus the probability that they did get a top 3 choice, given that they were matched. So I will do 1 minus. Now, I don't want to use the 79.2 if I'm using 1 as my total probability. So I would go back to the decimal, subtract, and I would get 0.208. Or equivalently, you could use 100% as your total, minus the probability that you did get a top 3 choice would determine the probability that you don't get your top 3 choice. So you could do 100% minus 79.2%, and that will be 20.8. Either way is fine. Would it be unusual for a randomly selected senior to be matched with a residency position and that it was one of the senior's top 3 choices? We found that probability already in part 1. The probability of a match and it being a top 3 choice was 0.743. That's the same as 74.3%. So now you have to go back to the probability scale and remember, probabilities going from 0% to 100% with equally likely events happening with a probability of 50%. So 74.3 is over here. It's between events being equally likely and being certain to happen. So this was on the side of things that is likely to occur. So would it be unusual? The answer to that would be no. In order to be unusual, it should be close to 0%, and our number is not.